Can we deploy a huge fleet of amateur telescopes to image a single planet? If the Voyager crashes into something, would we know? What's the point of studying gravitational waves? And Q&A Plus, does a starless galaxy have any planets? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are, across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Liam Dobbin. If we were to get 10,000 digital telescopes synchronized and focused on a particular star system, such as TRAPPIST, would they be able to collect enough photons to image planets? So there are two ways that you can add together the light of a bunch of telescopes. The one way is that you are adding them where you are collecting photons individually on all of the different telescopes, and then you are essentially using all of these data to reduce the noise and produce a better image. And if you took 10,000 digital telescopes and you imaged them at some target, let's say the Orion Nebula, and had them all gathering data at the same time at roughly the same conditions. So let's say you had them arrayed in a desert somewhere, 10,000 telescopes all looking at the same target together. Then you could stack up the images from all of those separate telescopes and you would be able to produce a better image, that you would have more data, less noise. It would make for a better image. But it wouldn't be enough for you to be able to, say, resolve something like the TRAPPIST-1 system, because what you need for that is resolution. Actually, for TRAPPIST-1, you also need to be able to block the light of the star, but you need the resolution. If you had 10,000 telescopes, it would be the equivalent of you having a telescope that is as big as the shared surface area of all of those telescopes. So if each one is, I don't know, let's say it's 10 square centimeters, then you would have 10,000 times 10 square centimeters as a sort of resolving area for your telescope. It would be a very big telescope, but it would be sort of roughly on the order of some of the bigger observatories on Earth. So that is the one way that you can do this. The second way that you can do this is you can build an interferometer. And this is where you separate the telescopes some distance, and then you tune the telescopes so that they're observing exactly the same wavefront down to the photon. So when you think about these photons, they can be 500 nanometers long. You've got to make sure that your telescopes are within 500 nanometers of each other when they're observing the light from the TRAPPIST-1 system. And it is incredibly difficult. But if you can do it, then you get a telescope with the resolution, the ability to pick out small objects that is the size of the separation between the telescopes. So it's less about the size of the telescopes and more about how far apart can you put these telescopes. If you put these telescopes on either side of the Earth, even two telescopes on either side of the Earth, you're going to make a telescope as big as the Earth, which sounds great, right? A telescope that is thousands of kilometers across. That would be a very big telescope. Now, it would only be able to see bright objects, only as bright as what that single tiny little telescope can see. And you had that challenge of making sure that they were dialed into a few hundred nanometers of each other. That's the challenge, that if a truck rolls nearby one of these telescopes, then it will no longer be within the nanometers of each other, and then it's off of the interferometer. But the other big challenge is the Earth's atmosphere. The Earth's atmosphere is this soup of sort of fluid air that is above the telescope, that is constantly changing and shifting, and puts a hard limit on how much you can see with any telescope. And so really, before the modern age of adaptive optics, which I'll go into in a second, there was really a limiter to the size, the biggest possible telescope. You could have a telescope that was, say, a meter across. You could have a telescope that was 5 meters across. And the images that you would get from the 5-meter telescope were not going to be a lot better than the images that you're going to get from the 1-meter telescope. It would be faster. You would have much more light collecting ability, but it wasn't going to give you that really nice resolution. It wasn't until the development of adaptive optics, where you put this artificial star in the sky, you calculate the turbulence in the atmosphere, you reverse that in your telescope, and you essentially make it as if your telescope is out in space. That was the big technology that unlocked the new mega observatories that we have around the world, the 8-meter telescopes, the 10-meter telescopes, the upcoming 39-meter telescope, they have to have that adaptive optics system to be able to see. So back to your original question, if you had 10,000 digital telescopes, each of which had a tiny little adaptive optics system so that it was able to remove the effect of the Earth's atmosphere. So each one of these little telescopes was firing a laser into space, and it was using that laser as an artificial star to be able to recalculate what the sky is supposed to look like. And you were able to arrange those telescopes to within a few hundred nanometers of each other, comparatively. So they were seeing light from the same star within a couple of hundred nanometers of each other. Then, yes, but all of those are engineering difficulties, the likes of which you don't even want to get into. So the short answer is no, that generally people build a big telescope. If you're going to build an interferometer, then, there are a couple of visible light interferometers, some infrared interferometers. They're very difficult to build, require incredible engineering. And I've done a whole interview about what it took to build this telescope called the Chara Array, which is an optical interferometer in the United States. And it is like the level of engineering is just off the charts. So you go with the brute force, 10,000 telescopes, all taking images of the same object at the same time, gives you more data. You can get a nicer picture more quickly. Space Geek Sherry. If Voyager crashes into something or is intercepted, will we know? Or will it suddenly go offline and be a mystery as to what happened to it? Yeah, it would be the latter. That if for some reason the Voyager crashed into an asteroid, then it would be expected to send a signal back home at a certain time, and it just wouldn't send that signal. And you wouldn't know whether you had lost the Voyager because it had crashed into something or whether its hardware had just broken down and it was no longer operational. And that happens all the time, where there are spacecraft, they're working fine, and then ground control sends a communication to the spacecraft does not respond. And then they try different tricks and techniques to try and bring that spacecraft back into communications. They'll try sending reboot codes. So even if the spacecraft is actually receiving the signals, but just can't return the messages, then it'll receive that, it'll reboot, and then it'll, it's like turning it off, turning it back on again, right? So these kinds of methodologies to try and bring back your spacecraft. And then if that doesn't work, after several weeks of trying, then the controllers will write off the mission, say, well, it lost contact and we are no longer able to communicate with it, and we can assume that it is lost. But we have no information. I mean, if Voyager crashed into a Kuiper Belt object 100 astronomical units away from us, we have no telescope that would allow us to be able to see that happen. It would just be, it didn't check in, it didn't reply, and it's gone. And whether it was an alien spacecraft picked it up, or whether it crashed into a Kuiper Belt object, or it just broke, we would never hear from it again. Deant6361. Will New Horizons end up leaving the solar system similar to the Voyagers? Yeah, now New Horizons is on an escape trajectory out of the solar system, and so it is going to leave the solar system in the same way the Voyagers. We have sent 5 spacecraft so far on escape velocities from the solar system. So Pioneer 10 and 11, Voyager 1 and 2, and New Horizons. Those are the only spacecraft that have been sent on an escape trajectory out of the solar system. And so they are going to head out of the solar system and begin orbiting the Milky Way as if they were stars. It's time to shout out our new patrons at the $5 level and above. Bruce, Eric Lindstrom, Corey Poole, R, Space Bear, Brendan Smith, Adam Walkus, Phil Reynolds, Zeke, and Cal Shumiacher. Join our community at patreon.com/universetoday. David Evans, would it be possible to use the radiation of space to power spacecraft? So it is theoretically possible. There's 2 kinds of radiation that you can get out in space. Actually, there's many kinds of radiation, but the ones that you're probably thinking about are the trapped radiation, the ones that are around, say, Jupiter. The other kind is, say, cosmic rays. These are high energy particles that have been sent from pulsars, from supernova, from supermassive black holes. They're the ones that destroy your DNA as they blast through your body, potentially giving you cancer down the road. It's this constant stream of these cosmic rays that are going through your body. So could you use those to power your spacecraft? Theoretically, if you had some way to be able to catch these high energy particles and then extract the energy from their velocity, then yes. But the challenge is that that is a very complicated thing to do. You essentially need to create a very powerful magnetic field to direct the particles as they are coming towards you. And then you would need to somehow decelerate the particles and then use that deceleration to provide electricity for your spacecraft. It sounds very complicated when you could just use the light that is coming from the star, which is a kind of radiation, and you are able to power your spacecraft. So although we could probably come up with some kind of engineering solution to extract some energy with a powerful magnetic field coming out of these cosmic rays, it would probably be a lot more trouble than it's worth, as opposed to just opening up your solar panels. And then the other way is the trapped radiation, the particles that are buzzing around the Earth and buzzing around Jupiter. And same thing, like theoretically, that those particles, as they pass by, they're going to induce a current in a magnetic field, right? You're going to get, if you have a magnetic field, you should be able to get some kind of electricity as these things are going by, but it's not enough. It's not happening quickly enough that you could really kind of count on it. Instead, you just use solar power. Juan Mendez, what is the additional value of gravitational wave observatories other than studying black hole or neutron star mergers? We are still in the very nascent stages of gravitational wave astronomy. And so the first gravitational wave observatories that were set up, the LIGO instruments, were designed to detect the most detectable gravitational wave events, the mergers of black holes that are in the sort of 10 to 100 solar mass range. That gives off a very specific kind of gravitational wave signature that is detectable by our instruments. But there are so many other kinds of events that produce gravitational waves that are just beyond the capabilities of the current range of observatories. So, as you mentioned, neutron stars. So once they were beginning to regularly detect colliding black holes, one of the hopes is you would detect colliding neutron stars. And that has since been done with the famous kilonova event. Probably two more other colliding neutron star events have been captured. But then you're looking for things like, say, a white dwarf colliding with a black hole, or a white dwarf colliding with a neutron star, or a star colliding with a black hole, or a star colliding with a neutron star. That would be very interesting. It would tell you about how stars are destroyed as they are interacting with black holes. But there's a limit to the size of the black holes that can be detected through the LIGO observatory. But the really interesting ones are the more massive ones, the intermediate mass black holes and the supermassive black holes. And because the supermassive black holes are so massive, so big, their mergers happen very slowly compared to the stellar mass black holes. The frequency of those mergers is beyond the capability of the current crop of gravitational wave observatories. But the European Space Agency is working on their next generation space antenna, LISA, which is going to detect the mergers of supermassive black holes. And that's really important because, one of the big outstanding mysteries that we have in astronomy is, we know that there are these supermassive black holes at the hearts of pretty much all galaxies, and that they were present early on in the history of the universe. And in some cases, the supermassive black holes seem more massive than they should be. If you imagine you start with a star, you get a black hole finds another black hole, they merge together, now they find other black holes, and you keep increasing, and the black hole's feeding on material. There's a limit to how massive a supermassive black hole you can end up with. And yet there are black holes that seem to have more mass than that. So there must be some other mechanism that is causing a black hole to be able to come together. Maybe. Or maybe they just don't understand, or maybe they're primordial supermassive black holes. We just don't know. But the real magic of gravitational waves, and the one that will be the gift that keeps on giving, is that gravitational waves are a completely different way of observing the universe from the electromagnetic spectrum. And so every kind of astronomy that we have done up until 2015, pretty much, was with the electromagnetic spectrum. You look at X-rays, you look at gamma rays, you look at radio waves, you look at microwaves, you look at visible light, infrared, ultraviolet. It's all the same thing. It's all just electromagnetic radiation. You're just seeing it at different wavelengths. And so the limitations of the electromagnetic spectrum, for example, not being able to see beyond the cosmic microwave background radiation, these are all the same thing. You're just seeing different aspects of the same kind of light. But gravitational waves are an independent system for being able to measure. And one of the most interesting things that you can do with gravitational waves, for example, is independently measure the expansion rate of the universe. That when you detect two black holes that are spiraling around each other and merging, the chirp, the gravitational wave chirp that you get allows you to essentially figure out the distance to this gravitational wave event. Now, right now, the accuracy is not as good as the other methods of measuring distance in the universe, but once it is very accurate, you'll know it is right in a way that you're still unsure with the electromagnetic spectrum. So that's one very exciting thing. The other exciting idea is that you'll be able to use gravitational waves to see beyond the cosmic microwave background radiation. So, we know that 380,000 years after the Big Bang was when light could finally escape out into the cosmos. And so you just literally can't see earlier than that because the entire universe was opaque. It was like the surface of a star. But the gravitational waves were passing through this material during this time. And so if we could make an even better gravitational wave observatory, it would allow us to see right to the Big Bang, that we'd be able to see seconds after the Big Bang, less than a second. We would detect the ripples, the oscillations of the universe as whatever incredible events were happening during the Big Bang. And this is, when it comes to electromagnetic radiation, this is a thing that is beyond us. It gives us additional ways to probe the vicinity around black holes as they're merging. You can detect supernovae that are asymmetrical. So if a supernova goes off and maybe blasts off one side of the supernova, like think about Mount St. Helens as it sort of detonated out the side of the mountain. If that happens with a supernova, then that would generate a gravitational wave, and that's something that you could detect. So I would say, of all of the applications of gravitational waves, the one that I'm most excited about is this idea of the primordial gravitational waves, the ones that get us earlier than the cosmic microwave background radiation, the ones that maybe allow us to see the Big Bang happening. That would be very cool. So there's tons more science that can be done with gravitational waves. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. And this week's bonus question, does a starless galaxy have any planets? I'll put a link in the show notes. All right, those are all the questions that we had this episode. Thank you, everyone who joined me for the live show, everybody who put your questions into the YouTube comments. I'm going to talk about Astronomy Cast, which is, of course, the long-running podcast that I am the co-host of. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Progetti, Barely Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailout, Dark Fingers, David Gilton, and David Matz, Evan Lindstrom, Evan.pro, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Filer Munley, Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Klatz, and Zeldemort Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. All right, I got a comment on YouTube that I wanted to read out and respond to from Carioja. Astronomy Cast. I don't know why Mr. Cain isn't promoting the podcast in every single episode here. Should happen, in my opinion. Why not try to get more ears and eyeballs to something that you participate in every week? It's just surprising. Pamela and her work would benefit as well. Fraser has a huge astronomy channel, while Pamela has been left with less visibility. And I'm surprised that you and Pamela don't do more video work together, or that you don't start this video empire together. I suppose everything has a reason. I'm guessing you started separately at first because working alone can be sometimes faster, but then Fraser at least ended up having a big team once the frasercain channel blew up. So if you're not familiar, Astronomy Cast is a podcast that I do with Dr. Pamela Gay, and she is a PhD astronomer, and we have been doing, and I always forget, 18 seasons, 19 seasons. We started in 2007 with really the deplaneting of Pluto and have been continuing on ever since. We just wrapped up episode 791, so we'll probably start into our 800s next season. Now, Astronomy Cast is great. We try to pick one different topic every episode and just cover it beginning to end, soup to nuts, dig down. So one episode on supermassive black holes, one episode on neutron stars, one episode on the moons of Mars, and so on and so forth, right? And we have never run out of topics, and I don't think we ever will. But the question you're asking is, like, why don't Pamela and I do more work together? And the reality is that we are separate entities. Pamela is a researcher who runs a citizen science project, an organization, a 501(c), so a nonprofit organization, and is a researcher at the Planetary Science Institute, and has her own company, her own team, and does her own thing. And the way Astronomy Cast happened 18 years ago was that I wanted to do a podcast with a co-host and reached out to Phil Plait, who is the bad astronomer and was a good friend of mine. And Pamela had already been doing an astronomy podcast, and she'd actually reached out to Phil Plait as well to do a collaboration. And Phil's like, I'm too busy. Pamela meet Fraser, Fraser meet Pamela. But I had been a science journalist now for 10 years, had been running Universe Today. I had multiple writers. It's my company. And I have been doing this job since then. And Pamela had her own organization. And this collaboration, actually, I don't pull a salary from this. I've never taken any money at all from the time that I spend on Astronomy Cast. My donation to the work that Pamela is doing is my time on Astronomy Cast. And then, of course, whenever Pamela is trying to do various fundraising projects, I will always participate for the hangout-a-thons and all these kinds of things they do to try and raise money for the work that they're doing, which is incredible at CosmoQuest. I donated our discussion forum to the CosmoQuest people so that they can continue on and sort of grow the community. So, but we are separate entities, like she has her own business and her organization and I have mine. And, it's great when we're able to do collaborations. We do them all the time. We'll meet up at science conferences or astronomy conferences and we'll do reporting together. We show up on each other's podcasts, but like in general, it's just a separate entity from what I do with my regular work at Universe Today. I hope that answers the question. All right, we'll see you next time.